So good evening. For those of you who don't know me, I'm Tim O'Shea, Principal and Vice Chancellor of the University. It's really a tremendous pleasure to welcome you to Professor Harald Haas's inaugural lecture. I'm particularly delighted that we have in the audience his wife Sibylla and his 4-week-old baby Anna, but also delighted to see senior members of court, members of the Board of Scottish Enterprise, and lots of students, and obviously lots of academic colleagues. So you're all very welcome here. Lots of excitement about the work that Professor Haas has been doing, and like you, I'm really thrilled to be here. He and I share a little bit of sort of evolution. I was asking him, as I always do to people who've gotten massively successful, when did you really start? He built his first hobby radio when he was 14, and I was building wee radios about the same age too. And for those of you, I'm looking to see, I'm not sure if there's anybody apart from Sibylla who is under 14. But if you were under 14, if you haven't built a radio yet, build a radio. No, it is seriously, it's a life-enhancing thing to do. So then Harald at the University of Nuremberg. Became diploma engineer and really developed the academic side of his wireless interest. He got his doctorate from here in University of Edinburgh in 2001. For a year, to the beginning of 2001 to 2002, he was project manager at Siemens for information and communication mobile networks. He then joined what's now the Jacobs University Bremen, and he was there for 5 years as associate professor of electrical engineering, and then really very happily for us and happily for his research, he returned to the University of Edinburgh in 2007. He holds 18 patents. He's published more than 40 journal articles, including a science article which has been cited more than 400 times, 130 peer-reviewed conference papers. And for those of you who aren't familiar with these sorts of domains, in a very fast-moving area like Harald's, an awful lot of the important publications are done as conference preprints rather than as journals. He's co-authored a book entitled Next Generation Mobile Access Technologies with Cambridge University Press, which has been translated into Chinese. He got a lot of prominence when the TED Global Conference happily came to Edinburgh earlier in the year. And since 2007, he's been a regular high-level visiting scientist supported by the Chinese 111 program, and in his case at the Beijing University of Post and Telecommunications. And for those of you who don't know, this is a very important program, similar to the Excellence Initiative in Germany, where a small number of highly important areas are supported. So I'm really very pleased he's here to give us the inaugural for his personal chair in mobile communications, which is entitled Shedding Light on Future Wireless Communications. Please welcome Harald.
Thank you very much. Thank you very much, Professor O'Shea, for the introduction and for your kindly hosting this event today. I'm deeply honored to be able to stand here today, and I would like to take the opportunity to say a few words of thanks, because it's not an event that doesn't happen every day. Particularly, I'd like to thank my wife, Sibylla, who has been patiently waiting for time to be invented and to be wrapped into a path to be given to her. Not yet there, but we're working towards that direction. Furthermore, thanks are due to Peter Grant. Peter Grant is the former head of school, whose encouragement, guidance has been of incredible value. And simply speaking, Peter is an incredible mentor and colleague. Also, I'd like to thank the current head of school, Alan Murray, for his tremendous support, as well as the current head of institute, Bernie Mulgrew, who accepted the innovation from Bremen in 2007 in giving us a home, me and my research team in IDCOM, and we thoroughly enjoyed at the moment. And I'd also like to thank Nicola, our secretary, who's basically made, through his tireless work, made these events like this happen. And finally, I'd like to thank my research team and my research sponsors for enabling me to pursue new research avenue in wireless and mobile communications. So hopefully I haven't forgotten anyone, but apologies if that is the case. I now would like to go through this presentation, and it's about wireless communications, mobile communications. And in the past, mobile communications looked like that, maybe, moving a few telephone boxes. But it's this person, at the moment, this was the past. The future looks like this, that we have about 1.4 million cellular radio base station or radio masts deployed worldwide. And we have more than 5 billion smartphones or mobile phones in use at the moment. And we noticed that the end of October was the time when the United Nations officially said we have more than 5 billion people on this planet. So basically everyone, almost everyone on average, has a mobile phone. And this is an increasing trend that people use mobile communications more intensively. And it's a utility like now electricity and water. We use it in our everyday lives, we use it in our professional lives, and it even impacts political systems, as we have recently seen. So it's so important, but if we look at it, how old it is, it's basically younger than I am. It's invented by a person, Cooper from Motorola, and this is the patent which describes the first radio telephone system in '73. So we have seen tremendous growth in that technology. And this growth is basically shown in that slide here, which shows from the year 2010 to the forecast in 2015, the number of bytes transmitted per month through our wireless systems. And you need to note the y-axis. It's called exabyte. Exa is a 1 and 18 zeros. It's a really, really, really large number. And you notice at the moment we have 0.6 exabytes, but the forecast is that basically is increased by factor 10 in 2015. So we need to note that a tremendous growth in data traffic that goes through these networks. And here you don't have to read the axis, nothing to read here. This is the radio frequency spectrum occupation in the United States from 0 to 300 gigahertz. You just have to note that basically it's a patchy landscape here. So basically every little piece of radio frequency spectrum, which is the means to do wireless communications, is already in use in some form or the other. It's really hard to identify new radio frequency spectrum for wireless communications or for communication systems at all, let alone wireless communications. So we need to remember there's little additional frequency resources we can gain. We have a tremendous growth in the number of smartphones and telephones that we see in the next few years. The data traffic increases. And what is plotted here, a slightly more complicated graph, is it's plotted here, the network capacity per device. Basically, if we take the radio communications infrastructure and basically divide by the number of devices, this would give us the capacity that could be carried per device at the moment. And then we see the blue curve, which is the forecast traffic that is needed to supply all this required data that these millions and billions of wireless devices would demand. And you see a clear trend. They don't go in the same direction. We need more traffic, more capacity than we have, and tremendously more. If you take the number, this is roughly about 40 megabytes per month per device. And what we actually need in 2014 is 1,700 megabytes per device. And there's a gap. There's a clear shortfall. So we are running out of spectrum. So this poses very interesting questions to me. First of all, are we using the existing radio frequency spectrum most efficiently for wireless communications? If we can answer that question, then we have a clue if it's a dead end or something can be done to make available new resources. But before we can answer that question, we need to answer, do we know what most efficiently is? And I humbly say, I would answer both questions with no. The reason why that is, I can show you here with a simple example. In wireless communications, we have a wireless transmitter. It's shown on the left-hand side here. It has a certain power it uses. And there's a receiver at some end, at the other end, and in between is a channel, a wireless channel. And that provides a gain, but the gain is less than 1, so it's essentially it's a loss. And there's a person that really helped us who invented information theory. It's Claude E. Shannon. He developed a framework that helps us describe and relate capacity. This is data rate, bits per second, with bandwidth, the radio frequency spectrum, the power that we use to transmit, PTX, and noise. And this is shown here. So this is the capacity, the number of bits we transmit or we can get from a certain bandwidth, a range of frequencies, from a certain transmit power at the base station perhaps, and some gain between the base station and your mobile handset, which is less than 1, and some noise power. So we can either increase the transmit power, we can increase the bandwidth, we can decrease the noise. These are the screws we can use in order to enhance the data rate per device. That's fine, that is limited, this is given. So we could answer, yes, we know how much data rate we would get. We just have to plug the numbers into this equation. But life isn't that simple in wireless communications because typically you have many links transmitting instantaneously. And we want to reuse the same frequency band resources we have, this frequency B, many times. And now we have suddenly the numerator here in that equation that gives us that link here, but suddenly something appears in the denominator of that equation. And simple mathematics, if something appears in a denominator, it makes the whole thing smaller. And basically this whole thing there at the bottom in red is interference. It's interference. It's radiated power from one device that basically comes to the receiver at the other end. And this diminishes the capacity. So the fundamental question now is, we can basically eliminate that interference by splitting that bandwidth B into 2 halves and give 1 half of the bandwidth to one link and another half to the other link. Then we wouldn't have interference. Or we could transmit simultaneously using the same bandwidth, but accept interference. The question is, what is better? And again, pose the question here, is it better to give each link half the bandwidth, so half that B, and have no interference? Or do we allow every link or each link to transmit on the whole bandwidth but allow interference? The answer is here on that plot, which again might be a bit involved, but you see a plane that sticks out of a red plane. The red plane is sort of the reference plane where both scenarios would be equivalent. But sometimes we are better off transmitting simultaneously on both links on the same bandwidth, and sometimes you are better halving the bandwidth and give each of them half and have no interference. But it depends on the deployment scenario. So it depends on the scenario, on these links between the transmitter and the receiver and the interference transmitter and receiver. And we want to have a system that basically autonomously would find the best situation when it uses the resources in what manner. But that isn't easy. Therefore, people have come up with a person called Vern McDonald in the Bell Labs came up with this concept that's called frequency reuse. You take that frequency B and divide it into n chunks, so 3 chunks, for example, 3 subbands, B1, B2, and P3, and allocate only 1/3 of the bandwidth to one cell, And you see that's what different colors. This is a cell, this is a base station where in the middle you typically have a radio mast, the antennas, and it covers a certain area. And typically this is a circle, but a circle wouldn't allow to cover entire area. That's why we approximate by hexagons. So we have 1/3 of the bandwidth in B1, B2, and B3. And what we can do is, in order to have a reuse of the same frequencies, we repeat that pattern as often as we wish. If you look like this, and suddenly what happens, there's no red cell adjacent to another red cell, no green cell adjacent to another green cell. There's always a ring of other colored cells in between, and that provides a static interference protection. So we don't have that problem that two links are very close to each other and interfere with each other. At the expense of, shown here in that red circle, assume this is an area of 1 square kilometer. Within 1 square kilometer, you use that frequency B2, that subband, only once. You can't use it there, you don't use it there, there. So we use that frequency less efficiently. But we provided sort of protection against interference. The problem is now if a smartphone, an iPhone, uses this entire subband B1 completely, then no one else in that area, in that circled area, can use it again. So what's the way out of this dilemma? How can we get it more efficiently? And the answer to that is to make the cells smaller. Take the same principle. Again, there's a red cell and it's only surrounded by a green and a blue cell. There's interference protection. Take the same area, and now you see that many red cells are within that area. So we can reuse that subband B2 many, many times. And therefore, we enhance the efficiency, so the efficient use of that subband B2. My daughter disagrees, but it's okay. So this is static frequency reuse. What we ideally wish to have is we don't split the frequencies into subbands. We want to reuse the same frequency in every cell so that we are not forced to shrink the cells, which comes at the advantage that we have to have many base stations, many cellular radio masts, many antennas deployed everywhere, and basically it's financially not manageable. Therefore, what we do is this, apply the same bandwidth in all cells, and then even have different levels of cells, different cell sizes. We call it macrocell, we call this microcell, and sometimes even we cover with one base station an entire home. These cells are called femtocells. So we have a hierarchy of cells, and we use the same frequency, but we have an enormous problem now with interference. And we get, so here is an example. This is an outdoor, a macrocell, and we have in street canyons, we might have these cells. In indoor buildings, we might have these cells, and we might even have smaller cells than these ones in different environments. So the problem is interference, and we need to get smart methods in place where the systems autonomously, independently find out whether they can use a certain resource or they can't. And we've been working in that area for quite a number of years with a big Japanese operator, and have developed a self-organizing technique, which we call the busy burst technique. And the way it works is demonstrated here very quickly. We have a base station that wants to transmit to that mobile station, so it transmits. So no problem, no interference. The link is fine, and everything is okay. The problem occurs if that base station wants to transmit to that mobile station here. That transmission from here to here, there's only a little difference between these two, would cause high interference at B. So what we do in order to prevent that case is that we let that mobile station transmit a little signal, like hello. And this is transmitted at a certain power, and that power can be measured all around that mobile station B, and it creates a so-called exclusion region. Now, before that base station starts transmitting, what it would do is it would just listen to that power it receives from that mobile station. And if that power is a buffer threshold, which would mean in turn that interference would be high if it would transmit. So it could then decide not to transmit and protect that link here. This is like a cocktail party. You go to a cocktail party, you talk to your neighbor, and suddenly somebody comes in very close to you and starts shouting. All communication is broken. But if you had a protocol that you, as a recipient of information, would at very given specified times say something like A, and that is then received by your potential interferer, and there's a policy of politeness in place that tells you if you receive that A at a certain level, you don't speak, because it would mean in turn you would interfere with an ongoing conversation. And then the ongoing conversation could go on, and you could basically use your smartphone to communicate with your partner, because that would essentially mean you would use a different channel but still would be able to communicate, but not using your voice. And that's the principle how it would work. So it's a self-organizing, polite structure so that all links in a network are protected, but we reuse if we can, or when we can. And that, in that case, for example, that base station is inside that exclusion region. It wouldn't transmit, it would refrain from transmission, so this one can go on transmitting. But let's assume that base station would have been outside that exclusion region. That would have meant, okay, if I'm transmitting, I would generate only little interference, so I can go on and reuse the same frequency and therefore enhance the spectral efficiency. And that is how it works. And here, what I've plotted here is the throughput, so that the data rate mobile would achieve on average. And here is probability. Say this is 10%. And here is sort of the benchmark, the old scheme. And here the black curves are the new scheme. And basically, only thing you need to know from this graph is that if that line here crosses the 10% or 0.1 line, that means that on average, you have the data rate that is guaranteed would be, in that case, probably 800 kilobit per second. So 90% of users would be able to get a data rate higher than 800 kilobit per second. But if we go to the black curve here, and again use the percentile here, with our scheme, it would be possible that a user would get more, 90% of users would get more than 5.5 megabit per second. So if you're in a hotel room or somewhere else, and if you get 800 kilobits per second, and you compare 5.5 megabit, I think it makes a difference in the service and the phones you're using. So we have clearly developed a technique that allows self-organized interference management in such networks. We have applied that scheme of reuse on a cellular level, but we can also apply it on a link level. Let's assume we have a transmitter here and one antenna and one transmitter, and this is the capacity, the number of bits per second we get for that link. Let's assume you have multiple antennas at the transmitter, and you have multiple antennas at the receiver, and we call that a MIMO scheme. Multiple input, multiple output. And we have a channel, and let's assume there's propagation through the channel, and there's effects like reflection, dispersion, so signals bounce backwards and forwards, and this produces a certain condition. Under certain conditions of that channel here, we can get higher capacity, and it basically increases linearly with the number of transmit and receive antennas, the minimum of which. So if you have 4 transmit antennas and 4 receive antennas, you can increase the capacity by a number, by basically 4-fold, 4 times. And this is plotted here in that graph, where we plot the capacity, which is the data rate, the bits per second that you can get using the one antenna and the transmitter and one antenna at the receiver. And you see at a certain so-called signal-to-noise ratio, you don't have to worry about the details here on the x-axis. But if we now introduce these MIMO schemes, we see that suddenly these graphs get higher and higher, and they get significantly higher. That means we can get significantly higher capacity on that link. The problem that we generate via this scheme is shown here. First of all, how it works could be illustrated by pipes. We generate multiple pipes between a transmit antenna and a receive antenna, and we transmit data through these pipes. But the pipes are not ideal pipes. There's leakage. There's leakage from one pipe to another pipe. There's leakage from one pipe to the third pipe, from that pipe to the other pipe, and basically applies to all of the antennas. Again, we come down to the concept of we reuse, but we buy interference. So we get a little bit of that signal from that pipe into here, and that causes interference, and we have to deal with that. And the way we deal with it is via signal processing. And here is what happens in a different illustration. So this is the first pipe that wants to transmit a symbol A, and it gets the A, but it gets also a little bit of B, a little bit of C, and a bit more of D from the other three pipes. We have the second pipe, which gets B, but a little bit of all the others. And this little bit of all the others is interference. So we have now smart algorithms that identify which symbol is the largest compared to all the interference signal. And let's assume we have smart signal processing algorithms that would be able to detect that A. This is the beauty of digital communications. Let's assume we can detect that A, which would give us a very unique advantage. We could then subtract that A from all the other links here. So interference would get less on in the other pipes. But first we would detect the strongest symbol and subtract from all others. So what would happen, we would have A, a clean A, and we would have a cleaner B, a cleaner C, and a cleaner D. Notice here, it's really hard to distinguish between D, C, and B. Yeah, it's relatively high, B and C. But now we can see C is very strong here. Maybe we can detect C on the third stream mathematically. Let's do that. And we can subtract C there and there. And suddenly, the second and the fourth pipe would get cleaner. Now, there's only one interference term we have to deal with in the second pipe. So we can detect B here, subtract from the others, and we have all symbols recovered at the receiver. That's why now we transmit in one go 4 symbols, A, B, C, D, instead of only one. So we have increased the capacity 4-fold at the expense of some signal processing. The problem here is that we have inter-symbol interference, the inter-channel interference that requires high computational power, and that basically drains the battery, and that causes all sorts of other problems. We need to synchronize the antennas. We need to have multiple RF chains, multiple transmitters, multiple receivers. And if we don't properly detect one stream and subtract an incomplete symbol from the other stream, we have error propagation. So again, we've been thinking about that and thought, how can we solve that problem? The main problem to solve here is how can we get rid of interference? And the way we got rid of interference is via a scheme called spatial modulation, which we've introduced and now happily see that it's worldwide accepted, and other places basically built on the concept we have developed there. Again, we have our multiple transmitters here. What we do is we split. So we want to transmit here our A, B, C, D, but we say that each antenna is also linked to a symbol A, B, C, D, a blue symbol and a red symbol. Now what we can do is we can transmit in one go a red symbol and a blue symbol by saying if that antenna transmits, that inherently means that a C is to be transmitted. I can show you how it would work. Let's assume that this is the symbols we want to transmit, and we would change between a blue and a red symbol. And that these two symbols are transmitted at one go, in one time instance. And it would, in that first case, in the first time instant, mean that we would transmit from the third antenna, because that is C. From the third antenna, we would transmit a red B. Yeah, that point here is a B in that constellation here. In the second time instance, at a second time instance, we would transmit from the fourth antenna, and we would transmit a symbol A, which is that point here, and so on. you notice at every individual time instance, we only transmit from one antenna, but we transmit 2 symbols at one time. So we have doubled the capacity, but have fully avoided interference. And that translates into a gain in the number of computations. These are subtractions, multiplications, divisions in a computer. And this is the classical old technique, and this is our technique, and we reduce it by a factor 6. So imagine you have a phone that now have a battery that lasts 6 times longer. That's the effect. We have less computations. Not only that, if we compare the transmit power, which is the blue one, transmit power of the blue one is the first scheme I've introduced, and the red one is our scheme, we can reduce the power by a factor 4, to 1/4. So we have less computations, less required transmit power because we have better signal-to-noise ratio, we don't have interference. And that translates to significant battery lifetime in your smartphone if you apply that, while you can still enjoy large data rates. So if you compare complexity, data rate, obviously the classical MIMO scheme I've explained first has high complexity but also high data rate. Then is the single antenna at the receiver and transmitter has low complexity but also low data rate. And we have low complexity and high data rate sits somewhere in the middle, but a practical solution which we are now trying to pursue in a project in China, UK-China Bridge project, where we try to commercialize that technology. So the key question is now, we've introduced techniques, and you notice it all boils around reducing interference, regardless how you view wireless communications. The question now is MIMO, multiple input, multiple output, be enough? And smart interference management, these two together, would they solve our problem of exponentially growing data rates per month? I say no. And here's some evidence that I'd like to share with you. This is the spectral efficiency gain that we achieve using different systems. These are practical systems we are here at the moment. That is the current system we have. In the future, we have this system and this system. This 2x2 means 2 transmit antennas and 2 receive antennas. And this is the efficiency in number of bits we transmit per second per sort of frequency unit, per hertz frequency. And you see a trend, it's saturating. So smart research is reflected in these systems here. These are practical systems. So we see that smart research doesn't get these curves exponentially higher, it saturates. So we only can use the existing radio frequency spectrum to a certain extent efficient. We can't grow the efficiency, the efficient use of radio spectrum outside what we have at the moment, and probably we end up with 1.5 or something. But we would need, if you remember, from 0.6 exabytes to 6 exabytes, we need a 10-fold increase of the efficiency. And this is really not possible with radio frequency techniques. That's why I've been looking into other ways, and I've been trying to think out of the box, step back, be limited in the RF box. Now let's look at the entire electromagnetic spectrum, where we have the radio waves. So this is the messy plot I have shown you at the beginning with these patches and so on. This is only one part of the electromagnetic spectrum. There's only also infrared. It's also part of the electromagnetic spectrum. There's visible light. So here, the light that's around us. There's ultraviolet light. There are X-rays, gamma rays. Certain frequency bands you won't really touch. Too dangerous. But in the middle sits something of a big value, of a big asset. No one really has looked at it. And I started looking into this 8 years ago with the advent of these light-emitting diodes. These are electronic devices which produce high light output. And they have other very interesting features. But if we look at the linear frequency range here, we compare the radio wave spectrum with the visible light spectrum. Guess what? This is not only free, it's not regulated, it's available everywhere, and it's 10,000 times larger than RF. And it's unused. It's only used for dumb illumination. We might need to make more out of it. And this is what we've been doing the last 2 years, funded by Scottish Enterprise. We turn this into an asset, not only an illumination device, into a wireless communications device. And the interesting point is we have spent a lot of money, or operators have spent a lot of money to install this infrastructure. 1.4 million cellular radio masts. But interestingly, we have 14 billion installed light bulbs worldwide, incandescent light bulbs. So the infrastructure is there, here, there, everywhere, light bulbs. There's no need to install more infrastructure. Just get rid of this bloody, the energy-consuming incandescent light bulbs and get more energy-saving light equipment into these sockets there. And we've done calculations. You can save more than 10 nuclear power stations if you just replace incandescent light by energy-efficient LED light. This is it. This is an LED light bulb. You can go and buy at B&Q and elsewhere. You won't get the best quality, but you get them, and they are used. And there are cities like Birmingham who have projects where they replace street lights by LED light because it's more cost efficient. So, what are the drivers for this visible light communication? Is the looming spectrum crisis that also the Federal Communications Commission in the United States has issued. The energy efficiency. A base station at the moment runs at an efficiency of about 5%. Most of the energy is wasted in cooling. Security, RF can be intercepted. We know that all the Google cars that picked up all the Wi-Fis in the streets. The availability, we can't use RF in aircraft cabins or underwater. But we have this tremendous advancement in solid state lighting, and there's cost. If you have many devices, then there's cost. And there's another basically hidden driver that we don't see at the moment, but will be coming. The Internet of Things. There are people that forecast that in the future we will have 7 trillion wireless devices spread around. And that means 1,000 per person on Earth. And that the driving force behind that is, again, saving energy, saving the globe. The amount of energy, the domestic energy consumption is about 30%. And most of it, if you think, is 10, 12% is for lighting and other purposes. The entire energy consumption of information and communications technology is 2%. So if we manage to get our homes, our stores, our universities more energy efficient, that would save a lot of energy. And in order to do that, we need to get smart environments. We need to have things that communicate with each other. If you go to the office, that your thermostat at the heating recognizes that you're in the office and then turns it on. And if you leave it, it turns it off automatically without human intervention. And that is smart environments. And this requires communications. It requires communication devices. And this requires light, in my view. So the Internet of Things is another driving force. And there are a few fundamental differences between radio frequency communication using incoherent light, and it's shown here, where in radio frequency we use the field, the electric field. We use complex values, and we only use signals that have negative and positive values. When we use intensity, intensity is power, can never be negative. It's only, therefore, unipolar. It can only be real valued. You can't transmit a complex number through light. It's impossible. And the information is carried in the intensity. And these are fundamental differences which require fundamental research and fundamental breakthroughs in order to make high data rate transmission possible using these devices. And we've been looking in that. This is the old classical way how your remote control at home works. You want to transmit a binary bit stream like this one, and you would, if you want to transmit a logical binary 1, you turn it on. The LED, if you want to transmit a 0, you turn it off. That's a transmitter. What you see at the receiver is something like that. It's distorted because of all sorts of distortions on the way from the transmitter to the receiver. And what you would do, you would introduce a threshold, and you would decide at every instant, is that value above the threshold after you have synchronized, and then you would decide, yes, above, so it's a 1, it's a 0, a 1, a 0, and that's how you would regain the capacity. But you would only, in terms of states, you have two. You have on and off on the real axis. That's all you can get, like the Morse alphabet. And if you remember the very basic equation at the beginning, capacity scales with a signal-to-noise ratio. So that means the signal power. It doesn't matter if that point is here, or in the roof, or in the sky. As long as it's above the threshold, it's a 1. It's only a 1. It's only 1. So we really can't scale the data rate with the signal power we have. But if we use visible light communication, we have lots of signal power, and we want to make use of that. So this isn't working here. So that's why we came up with a smarter technique. Again, I like pipes. Now the pipes are in the frequency domain. We have frequency pipes. And we have now a constellation diagram, which is like the English alphabet, where you not only have on and off, you have A, B, C, D, have a richer alphabet, where one number basically carries 4 bits in that case. And now we have not only the real axis, only the 2 yellow points, we have 16. And if we have very good signals, we can have 64. And if we have even better signal, we can have 1024 of these yellow dots split there on the axis per channel. And then if we have a magic operation here, which is not really magic, it's called orthogonal frequency division multiplexing, which generates from this complex set of numbers a real valued signal that looks like that. It's varying in intensity quite heavily, a problem in RF, because in RF you don't want to have variations in the amplitude. But when I looked at it as a problem in RF, I thought this is a big bonus in intensity modulation, where we modulate only intensity, because these voltage variations, if you want, or current variations, can be turned into intensity of an LED light bulb at a speed that is not recognizable by the human eye. And the way we can scale it is sort of shown here. Instead of transmitting 1 bit, we transmit, in that case, 16, and that, via a standard equation, turns into 4 bits. So that's why we have these 4 here. 4 times mu, if we have mu frequency pipes, we have 40 bits instead of only 1 bit. We've increased the data rate 40 times. And that could be even brought to higher increase if we have very good signal. Now, suddenly we can make use of that gamma here. Suddenly we can scale the data rate with our signal. And that is basically giving us a new dimension, a new possibility in using these light bulbs. In that case, 4-fold increase. And we can take this signal here that we get from that magic operation, and here we see the input voltage of an LED, and this is the output intensity with different colors. We just impress that signal onto the LED curve, and then you see this peak would be high intensity, this peak down would be low intensity. So we vary the intensity of the LED very rapidly. And in the lab, we have now achieved 124 megabits per second in real time in ambient light conditions. I think it's the fastest real-time system that uses standard off-the-shelf LED light bulbs that achieves that data rate. And what does it buy us? It would buy us, you have a Wi-Fi router here, wireless LAN, and it gives you 52 megabit per second. And what I've shown you, a light bulb from Farnell, 3 pounds, gives you twice as much. Not only that, if you think what that is made of, it's made of an RF unit. It's made of a housing and signaling lamps. It requires an AC adapter. It requires cables for hooking up the AC adapter. It requires cables. Now, we can throw all this in a bin. We don't require that because a light bulb is supplied by power. We don't need the power cord. We don't need the DSL connection. We can get rid of this. Develop a microchip, again with my colleague in informatics, Nigel Tom and Björn Franke. It's an EPSRC project. We try to develop such a microchip that is then simply fit into a light bulb, and there you are. 120, 200 megabit per second, and my research goal is 1 gigabit in 12 months. And that's it. So we have done research with the Airbus in Germany and have then calculated the signal, this gamma that I've shown you in the equation. This is now shown here in graphically. There's a light bulb here, and that's basically high signal, low signal at a corner, even lower signal, low signal there. So we want to generate maps of data rate. How much bits per second can we transmit at what location in an aircraft A380 cabin? That was the question. And here's the answer. If we distribute wireless access for optical access points in an aircraft cabin, then we can now fully determine what's the data rate at what point in the cabin. And we have different ways of doing it and different colors show you their trade-offs. I'm not going into detail here. But it gives me now basically the pleasure to introduce to you the potential applications that might bear this technology. It can be used in aircraft cabins, obviously, and not only to provide multimedia access and wireless access, cellular access in an aircraft cabin, but also what aircraft manufacturers are interested in is reducing the weight. Every wireless system reduces cables and reduces weight and makes cabins more flexible. It can be used underwater. Now divers can communicate, exchange images. RF doesn't work underwater. Ultrasound is too slow, but here we can achieve megabit per second underwater. Petrochemical plants, not possible to transmit wireless there because of sparks and so on. In hospitals, making better, more convenient wireless equipment, introduce that to hospitals. Another, and to manage the high volume of data that is generated in a hospital, to playing the security card here, because again, these signals, they don't penetrate through walls. It's more secure than in RF. And in the traffic management, intelligent traffic management systems to avoid, again, energy consumption. If the light here is red, you can turn off the engine via the light. Or you could use the front light of a car and the back light that they communicate. Cars can communicate with each other, thereby preventing accidents. It's much faster in reaction time, such a system, than any human is. Or we can have these shopping lights where shop owners can broadcast the latest thing on sale via the window light. Museums that use light to illuminate an object can not only illuminate the object, provide information about the object via this technology. So the applications are beyond my imagination at the moment, and I feel that there is something radical there that we can use. Street lights could be wireless access points. Remember, the way of increasing capacity is getting smaller cell sizes. Here you are, small cell sizes. Every lamp is a small a small wireless transmitter, providing hundreds of megabits wireless access. So this is all. I'm glad I don't see too many sleeping faces. This is the end of my boring theoretical and slide presentation. What I'd like to show you now, hopefully, something that we've developed in the lab. It's a drop here. What we have here is a desk lamp. And inside that desk lamp is an LED light bulb. And behind there is a tiny equipment. Not really, it's big power supplies and an evaluation board, an FPGA board, which has all these hopefully smart algorithms implemented. And if I turn on the light bulb, you hopefully see that I have light to create my next exam paper. But not only that, it's a high definition video that is transmitted through that light here, through that LED light bulb. And you see, if you look at the light, it doesn't change. You don't see flickering. The changes of the intensity are so rapid, it is normal light. And the question is, do we have to have the light on all the time? No. Thank you. No, we don't. We can dim down the light and then still transmit wireless signals. Because if you remember this time variation signal, depending on where you place it in the LED transfer characteristic, it would determine how bright that light is. And if you want to have low light, you would basically put it down at the bottom level as much as possible. But I can show you that it works if I do that. There's no video transmitted. So it really goes through the light. And if I release it, get it back, it's the video that has gone through that light. And that's a 3-pound Farnell LED light bulb. Every student can buy it, have a little project tonight, and develop that at home. Tomorrow morning, I collect the papers. I've had many comments of saying, yeah, this only works in line of sight, but I want to get this comment across here. It also works in non-line of sight environments as long as enough light. And enough light depends, we can use even low energy via our scaling mechanisms for that gamma. This is by design made line of sight so that I can show you do that. But if you have it in the ceiling, if you have different light sources, it would also work if your smartphone is underneath the chair. And I also get the question, what happens if you get ambient sunlight? I'm not able to hold the sun in my hand, but I have a high brightness LED headlight that produces constant light. Can I interfere it? I'm holding it directly into the hole where the receiver is. It really doesn't interfere with the transmission. So constant light doesn't really hurt us. So we can have the sun walking by the receiver, or even we can make it flash, so it's really bright. Flash into the hole. Only if I do that, it stops. So we have developed that. We are at the beginning of a startup company that will be in operation in January. And my dream is that every light bulb in the future will carry a little microchip with our technology inside. And it's then not Intel inside, it's VLC limited inside. That's our future vision. And with that, I hope I have not exceeded the time too much. Thank you very much.
I'd like to ask you all to join me in thanking Harald for, and I can't resist, that wonderfully illuminating talk that you have given us today. And note that I am head of college here, and I have to say when I come to inaugural lectures like this, it makes me very proud to be a head of college. I feel like a mother with all her children and they're doing really well. And Harald, you've a hard act to follow. And we wish you all the best for the future. Keep thinking outside the box, please, for us all. And all of you, when you go home, remember you've got your homework. So you've been charged by the principal that you've got to build a radio tonight. And you've been charged by Harald to go and buy one of these lights and develop that yourself. So you're going to be busy. So don't spend too long here afterwards. And I expect you all at my office at 9 o'clock tomorrow morning to show me the results of your works overnight. But anyway, please join me in thanking Harald for a wonderful talk here this evening. It's been truly inspirational. Thank you very much indeed. Thank you.